Hello, can everyone hear me okay? Great. Sorry about the late start today. I'll go ahead and begin. There's a lot of material to cover for this week. So what I'm going to do, because there were requests to go into more detail on certain topics, for today, I'll cover linear regression, decision trees, perceptrons, ensemble methods, and I think that's it. And then next week, I'll reserve for SVMs and naive Bayes. Oh, I'm echoing. Okay, 1 second here. Let me see what's causing that. Okay, why am I echoing? Here. Am I still echoing? All right, we just had one more person join the chat. Let me know if I'm still echoing or if the sound is okay. Just looking through everything, making sure I don't have another tab open that's causing it. I don't see another tab. I just see with a 1. All right, give me just 1 second here. I'm going to close some things and then reopen them. Don't want to record this when there's an echo. It might be. Unfortunately, I think it's only the two of us that are in the chat. I'll go ahead and begin because I don't know what's causing the echo. If there are any questions, I'll try resolving it afterwards. That's just because I'm 10 minutes in already. I'll just go ahead and begin. And I'll try to speak slowly so that way it's not too unbearable. Jumping right into it, we'll begin with linear and polynomial regression. In a nutshell, linear regression, as the name describes, is when your data can be drawn out in a bunch of points. Let's say that you have 2 features that you're trying to fit a line to, such as, let's say for this example here, you have time as one feature and price as another. And let's say that the data itself looks very linear. Then what you're going to try to do is fit a line with the equation y equals beta 0 plus beta 1 times x, and then try to modify beta 0 and beta 1 such that the line best fits the data. In order to verify that the line is the best fit, what we will try to do is try to minimize the distance between the points themselves and the line. Actually, see if I can put this in a presentation form. So you want to minimize the distance between the line and the points by modifying the value of beta 0 and beta 1, and we want to modify these values automatically. Oh, that's good to hear. All right, so it's hopefully there's no echo for anybody. So the techniques that we use to minimize, to update beta 0 and beta 1, so there's a lot of, first of all, you have to choose a metric that you're using to minimize in order to make the line reach the point of best fit. The most popular would be sum of squared errors or sum of absolute errors, where you take the distance between each of these blue points and to the line. And then you just try to take the sum of all of those distances and then try to move the line such that it minimizes the sum of those distances between the blue points and the line itself. The lines being in red here in this graph. One of the most popular ways of doing this is using gradient descent to minimize the error. You can think of gradient descent as, let's say that we start off with a horizontal line. Then we update the line by asking it for each point what the distance is. And then we adjust beta 0 and beta 1 by a small amount to make that error smaller. We do this by multiplying. So I believe in the class they went through two different methods. Let's see if I can remember the names here. They did the sum and then the absolute sum, I think they were called, which is essentially what you do is you take the error and then you use the error to change the value of beta 0, and then you take the horizontal distance from the point to the origin, and then you use that to modify beta 1. If you were to actually graph out these changes, the change in error, you would find that it would generate a sort of parabolic shape like this. And in order to get to a minimum, so like let's say you start off on the far left of this graph with a random initial value for beta 0 and beta 1. As you adjust beta 0 and beta 1, the error is going to increase very rapidly at first as you're modifying the values of beta 0 and beta 1. But eventually the change will get more gradual and gradual until you hit a point of minimum for the error, which is when the line will be of best fit. And you can control how quickly you move along this line using the learning rate. Something to think to worry about when you're messing around with gradient descent is that there are such things as a local and global minima. A local minima. So let's, in this graph here, if our error can be visualized as being completely parabolic, then the minimum down here is the global minimum. But if we had a different shape, let's see if I can find one here. Do I have a picture? I don't. Okay. If it were not parabolic in shape, but more complex, such that there were multiple minimum points, Each of those points where you can minimize the data would be considered a local minimum. But the lowest point would be the global minimum, if that makes sense. I wish I included a graph of this here. Let me see if I could find one real quick on Google. Yeah, so taking a look at this graph here. You notice how, I'll wait for it to load. You notice how there are two valleys here. There's two blue valleys where it's color coded such that the higher up it gets closer to red. As it gets lower, it gets closer down to blue in color. You notice in this graph that there are 2 points that are in blue. Both of those would be considered local minima. However, the value which minimizes loss the most would be the global minima. When you create your algorithm, when you perform learning steps, when modifying the values of beta 0 and beta 1 to adjust your line to best fit the data, you need to make sure that you're hitting a global minima and not a local minima. When you're just dealing with a single line, that's very easy to do. But when you start coming across more complex problems, such as polynomial regression, where you have more complex lines that are trying to fit the data, and you're trying to modify. So with polynomial regression, it's no longer just y equals beta 0 plus beta 1 times x. You can add plus beta 2 times x squared plus beta 3 times x cubed plus so on and so forth up until beta n times x to the power of n. And that can, by modifying each of those values of beta, for which you can have quite a lot, you will generate more complex lines, which can cause you to hit local minima when you're trying to find the line of best fit. Are there any questions so far? I'm hoping I'm not being too confusing regarding that description. In order to calculate the minimum, there are several ways you can do. There are several methods you can use. One of those is the MSE cost function. It's a convex function, so it has no local minimum, it just has a global minimum, and it has a smooth slope. Remember, the cost function is what you're actually using to minimize the error between the line and the points here. So it's the equation that you're using to generate this red line here. So when we're trying to generate our cost function, we want it to be convex. That way we don't have to worry about a local minimum, and all we have to do is constantly decrease the error to reach that global minimum. In order to make sure, so that's just going through it. Regarding training your model to take those steps towards reaching that global minimum, there are many ways in which you can read the data. The two extremes would be batch gradient descent and stochastic gradient descent. Batch gradient descent is using the entire training data at every step, in which case, if you have a lot of data, it can take a long time for you to train your model. In contrast to that, there's stochastic gradient descent, which is picking a random instance in the training set. So picking one data point, and then at that step, computing the gradient, which is that distance, basically passing the error through the cost function, and then minimizing that error accordingly or adjusting your line accordingly. When you're doing it a single point at a time, your algorithm can perform much faster, and it allows the algorithm to run better on larger training sets. So in between batch gradient descent and stochastic gradient descent, it's not including on the side, is mini batch gradient descent, which is training on not just a single point, but on multiple points at a time. And then adjusting it. So it's kind of getting the benefits of both worlds of batch gradient descent and stochastic gradient descent, where batch gradient descent is great because it reaches the final or the best result after a single computation, versus stochastic gradient descent, which gradually will reach the answer. So linear regression is pretty widely used and it's pretty well understood. It's easy to use because minimal retuning is required. All you're doing is you're modifying the values of beta in order to make the line better fit the data. It is highly interpretable, meaning that it's easy to explain to others, and it's the basis for many other machine learning techniques. The downside to linear regression, though, is that it's too simple. There must be a linear relationship between independent and dependent variables in order for it to work, and it's very sensitive to outliers. So if you take a look at the two graphs down here, the one in blue includes outliers, and the one in red omits outliers. Outliers are points that are extremely far away from the data. So in this example here, where the outlier is directly in the middle of the data, it doesn't have much effect on the resultant line. However, if the outlier, as you see in the lower right picture, the outlier exists in the upper left of the graph, away from the rest of the data. So while everything else, excluding the outlier, can be fit pretty linearly, if the model detects the outlier and tries to adjust for it accordingly, it can really throw off your end result. As you can see here, between the red line and the blue line has, in the lower right graph, has adjusted itself to a noticeable amount to account for that outlier. The best ways to avoid this would be to either clean your data beforehand to remove any outliers that could possibly affect your data, or to simply choose another model that's less sensitive to outliers. We spoke about this a bit earlier, but going over it again. Polynomial regression, more complex than linear regression. The highest degree of line that you can create would be equal to the data size, at which point you would try to generate a line that would hit every single data point. However, if you hit every single data point and make sure every single point fits the line, you will be overfitting with the data, and your model will be very brittle to any new incoming data that's coming in. So you don't want the model to hit every single point. You just want it to encapsulate the overall shape of the data, or of the training data. That way, when you actually use it on the test data, it's not so sensitive to noise. Are there any questions on linear regression or polynomial regression before I continue on to perceptrons? Okay. Perceptrons on a high level are modeled after neurons in the human brain, where they take in many inputs and produce a single output. In this picture here, you can think of each of the white circles containing a value which it multiplies the input by, and then each of the arrows are being summed up. So in that left image, you have 4 inputs that are being multiplied by 4 numbers. Then the sums of those products are then multiplied and then output as the final result. Perceptrons are the simplest form of a neural network. With the perceptron, you're only looking at one node. So this example here, this image from the video shows, as an example, where you're passed in 3 features. You have a test value, which is 7, a grades value, which is 6, and a bias of 1. A bias is, you can think of as a constant that you're adding to the input features. So if this model had 2 input features, which let's say you're trying to determine here the goal here is that you're trying to determine whether or not you should accept or reject a student into a school. So you're looking at their grades, and you're looking at how well they did on tests, and you've assigned a value to their grades overall, and you've assigned a value to how well they've been doing on tests overall. As you can see in the center bubble here where it says score is equal to, what we're doing here is we're multiplying the test score by 2, and that's the weight for the test score. We're multiplying the grades by 1, so the grades we're taking linearly. And then we're multiplying the bias by 18, or by negative 18. And what that's doing inside of the model, let's see if I can find it on the video here. Yeah, is that inside of this model, we are trying to generate a linear boundary. That's what you're doing with the weights that you're multiplying by, is that you're essentially doing linear regression in a more complex level. So whereas linear regression was more trying to predict a number, this is trying to perform classification, which is trying to find a boundary line and classifying objects along the boundary line. By modifying the weights of both the input features and the bias, you're changing the slope of this line here to better encapsulate your model. I believe one of these images encapsulates pretty well. Yeah, here you go. So for each of your inputs, let's say you have n inputs denoted here by x. You then multiply them by the weights w, and you add your bias b, and that will generate a linear function internally. When you visualize it, you won't necessarily see this linear function. You only see the results of it, which is the classification of, in this case, a binary classification of yes or no. And so what you do is that you pass in the values, and it will spit out a number. You then have to pass that number through an activation function. In this case here, we're using a step function. The step function, or the activation function, is what's actually performing the classification. In this case, it's a binary classification. It's either converting that value on the line to 0 or to 1, and then using that value of 0 or 1 to classify accordingly. Oops. Perceptrons themselves are components of neural networks. A neural network is essentially many layers of perceptrons. So perceptrons themselves are very useful to know, and they're very useful overall. Regarding the activation functions, there are many that you can use that are covered in more details in the videos. You have step functions, sigmoid functions, softmax functions. There's a lot of them. Perceptrons are great. While I was talking about them in the classification sense, depending on what activation function you use, you can use them as well for regression. That is, rather than trying to predict a yes or no question, you can use it to output a number. Perceptrons are great for you working on tabular data sets. However, you must be careful, especially when dealing with neural networks with many perceptrons in it, that they are prone to overfitting. There are many techniques that you can use to prevent overfitting, which will be gotten into much later in the course. With that being said, are there any questions with how perceptrons work overall? Okay, moving on to decision trees. Decision trees, we have kind of come across an earlier example of a decision tree when we worked with the Titanic data set. That is, we had multiple features such as gender, age, what class, how many siblings they had, and we tried to use all of that data to generate a decision tree, which is given that the person was less than age 10, we determine whether or we said true if we decided that they would survive, or false if we decided that they would not. Given that they're less than 10, we then try to decide whether or not they were male or female, and then we'd try to decide whether or not they were higher class or lower class. Within this tree, A, B, C, D are the decisions we're reaching. The tree itself can be extremely complex with many answers. Not only that, you can ask as many questions as you want, which will affect the depth of the tree itself. Give me 1 second. Sorry about that. Now, with the Titanic problem, we generated a decision tree by hand, which is to say we chose which questions to ask. But that's not true machine learning. With machine learning, what we want to do is we want the model to generate itself based off of the data that it is given. In order to do that, we'll have to cover entropy. You can think of entropy as measuring how volatile the questions being asked are. So in this example here, and this is covered in the videos, I'll just go over it very quickly. Let's say that you are given a bucket, and in the bucket are 4 balls, and the balls are colored either red or blue. If all of the balls are the same color, we want our entropy to spit out the value 0, which is to say that if we reached our hand into the bucket and grabbed any ball, then no matter what we did, the result would always be the same. Versus the second option, or versus the bottom option here, where if we have 2 red balls and 2 blue balls, what we want to do is we want a higher entropy value to symbolize that if we reached our hand into that bucket and grabbed a ball, we are much less likely to know what ball it is we'll be grabbing out of the pit or out of the bucket. So if we know for certain what the result is going to be, the entropy is 0. If we are extremely uncertain, the value is closer to 1 for the average entropy. That's what we want as the final result here. And we would prefer the model that has smaller entropy. In order to calculate entropy, what we do is we perform a negative log on the probability of the result. So let's say here that we want to predict the probability of grabbing a ball. In the first example, where all the balls are red, the probability of grabbing a red ball is 1. So if we multiply the probability of grabbing a red ball 4 times together, you get 1 times 1 times 1 times 1, which is 1. And then all we do is that we take that probability of grabbing a ball 4 times, and we just take the negative log of that. And that's the function, that's the entropy algorithm. So in this bottom equation here, or the bottom problem, the one with the highest entropy, because the probability of grabbing a red ball with replacement each time is 50%, you get 50% times 50% times 50% times 50%. And then we take the negative log of that. And so this is log 2. So you'll get 1 plus 1 plus 1 plus 1, because negative log 2 of 0.5 is 1. And then you sum that up, and then for the average, you divide it by how many times you reached in with replacement. So in this case, it's 4 times, and the average would be 1. All right, are there any questions on how entropy works? Okay. Now, the reason why entropy is important is because when we come back to our decision tree here, what we're trying to do is we are trying to ask ourselves, how do we design our decision tree such that we ask the fewest amount of questions possible in order to reach our results, right? We don't want a decision tree of infinite depth. We want, if possible, a decision tree of one depth or as fewest depth as possible, which means we're asking as few questions as possible to reach our result. We want to create our tree such that we do that. So we want the first question we ask to be the most important question. So that way we can filter out the most information. And then the second question we ask to be the second most important question to cipher out even more information, right? So what we want to do is we want to generate a decision tree that has low entropy if possible. And we can determine how well our decision tree performs by using the information gain. The information gain equation is equal to the entropy of the parent, the first question being asked, and then 1 over the number of questions that you're asking times the entropy of each of the children. So in this case here, the parent has 2 children. So that's the entropy of the parent minus 1 over 2 times the entropy of child 1 plus the entropy of child 2. And that will give us a scalar value for the information gain. And that information gain tells us how well that decision tree is performing. Does that make sense? Okay. With regards to the benefits of decision trees, like perceptrons, they can be applied to both regression and classification problems. When I say it can be applied to regression problems, you can think of it as essentially coming to the decision of a value instead of coming to the decision of a classification for the tree itself. Decision trees, depending on how many questions you ask, are also prone to overfitting. But you can prune the number of questions being asked or the sensitivity of the questions in order to reduce this. Finally, because we can see what questions are being asked, decision trees are great for visualizing how decisions were made. The final model we're going to be talking about today is ensemble learning. And ensemble learning asks the question of why should we learn one classifier when you can learn many weak classifiers at once? So you generate an ensemble of predictors, and then you aggregate the answer from those predictors. It's one of the most powerful machine learning algorithms available today. The Netflix prize-winning algorithm used ensemble method. So I didn't go over this, but in the videos that talk about random forests are essentially an ensemble of decision trees. Now, there are many ways you can handle aggregation. So it could either be hard voting, which is you take the majority vote. So if you have 10 ensemble methods, all trying to perform a binary classification, and if 6 of them vote one way and 4 of them vote the other way, by using hard voting, you go with the 6. You can use soft voting. You can use mean value from how the decisions are reached from all of them. There are many ways which you can handle the aggregation itself. And ensemble learning, like the rest of these methods, are available within the sklearn library. So why use ensembles? Ensembles have very little overfitting because you're using a lot of models all at once. There's lower error. It's just great overall. So in this case here, what we have is we're taking in a neural network, we're taking in a linear regression model, we're taking a decision tree model, we're taking an SVM, and for each of those models, we're taking the mean of all of the results and using the mean of all those results for the output Y. And then just trying to visualize it better here. In this picture, we have the data which can be visualized as these green dots here. And let's say we took a bunch of polynomial regression models, and we trained each of those models to try to hit as many of the points as possible. So in this case, there are 5 models. Each of the models in themselves are fairly bad at making a prediction. So if you take a look at model 4 here, you can try to follow the line on the bottom, and it just kind of goes all over the place trying to hit as many points as possible. The ensemble in blue will take the aggregate of all of those lines and combine them into one, which, as you can see here, is a much better fit than any of those models individually. Going into more detail regarding the aggregation, as I went over beforehand, hard voting is talking about the majority of the votes of all the classifiers. Soft voting is if all classifiers are able to predict the probabilities. So if they have a predict probability method, then what you can do with sklearn is you can predict the highest probability averaged over all of the individual classifiers. So it's soft because you're using probability rather than doing majority vote. And you can use mean or average values for continuous problems. So going into bagging next. So bagging uses the same training algorithm for every predictor, but trains them on different random subsets of the training set. So looking at the data down here, in the bottom 2 images, we have on the left-hand side just a regular decision tree trying to go through all of the data and trying to train a model given all of the data all at once. And from that, generate a decision boundary, with yellow being on one side of the decision boundary, blue dots being on the other side of the decision boundary. Now, if you gave the decision tree only a subset of all of that data, what you'll do is you'll reduce the amount of overfitting and generate a much smoother line, as you can see in the lower right. Now, this scales very well. The predictors can be trained in parallel, which is to say that you give the predictors different subsets of the data, and you can process this using different CPU, GPU cores, or even different servers. And it's a great way to just generate a bunch of individual weak models with the subsets of the data, and then aggregating each of those models together in order to generate a better model overall. Are there any questions on bagging? All right. So going on to boosting. So taking all of those weak learners we just created using subsets of the data, we can combine them together to create a strong learner. And so what this does is that it takes the data and then it trains each of the predictors sequentially, with each trying to correct its predecessor. And it keeps doing that until it generates a better model overall. There are many powerful boosting methods available, such as ADA boost, gradient boosting. All of these you can look up in more detail on sklearn. But using boosting, you'll generate a lot of powerful predictors. Something to note about boosting as well is that it cannot be parallelized. So it doesn't scale as well on its own as bagging does. And on the bottom here, I've sort of outlined the process. So the base learner initially takes all the distributions and assigns equal weight to each observation. And then the learner pays higher attention to observations having the prediction error, then applies the next-based learning algorithm. So it sort of cycles through each learning algorithm. And then it iterates that method until the limit of the base learning algorithm is reached or a higher accuracy is achieved. So if it doesn't achieve a higher accuracy, then it will just use the previous model. As an example of this is ADA boost right here. So the predictors correct the predecessor by paying more attention to the training instances that were not correctly classified. So what that means is that if the first, let's say we have a bunch of weak models, okay? By weak, we mean that the models have high error. So the first model that we come across misclassifies a point. Then we apply a second model, and let's say that second model correctly classifies the first point. What we do then is that the relative weight of the misclassified instances are increased. So we punish the models that are misclassifying more points. And we reward the models that are classifying more points correctly. We then use the second predictor to use the updated weight and make predictions on the training set to update the weights again, and so on. And at the bottom here, I've included some code from sklearn as to how to code an ADA boost classifier using a decision tree as the weak classifier. All right. That's all the slides I have for now. So next week, what I'll do is I'll go into more detail regarding SVMs and naive Bayes. Before I end the session for today, though, are there any questions regarding any of the material covered so far? Any questions on linear regression, polynomial regression, naive or ensemble methods, perceptrons, decision trees, random forests? Okay. Well, if there are no questions, thank you for attending. I'll be posting this video on Slack afterwards. If any questions come up afterwards, feel free to either post them in the Slack channel or message me directly. Yeah. Otherwise, for this week, just try to get through as much of the material as you can. If I'm going too fast, please let me know. If you want me to go into more detail next time, I'll try to slow things down. I know I went through a lot of topics today. Other than that, I hope you have a good week and good luck with the material. I'll see if I can also get a head start on the Finding Donuts project next week as well, if this pace is okay with everybody. All right. Have a good night.